Hello, my name is Abhimanyu Singh, and I'm going to present the EV ADA System Embedded System Internship Project and MRTech Technology Bangalore. So, this is the PPT generated by both of us, Mahendra Pratap Singh and Abhimanyu Singh. We are both are student of BTech Arya College of Engineering IT and in third year from the ECE branch, Jaipur. So let's start from this. We will going to introduce what kind of dashboard we are using, what kind of software simulation we are using. So first of all, let's start about from our microcontroller. We are currently using STM32 Bluepill microcontroller. Continuously monitor the vehicle parameter and provide real-time safety alerts through an interactive dashboard. So basically, we use this STM32 Blueprint on the Pixim Lab, which is look like this. So it will help us to live speed and battery monitoring, motor temperature tracking, driving range estimation, collision warning, blind spot detection, UART communication, Python dashboard visualization, and many more things. So yeah, we program the thing on the software which we call as Workspace 19.9 EV-dash STM32 Cube IDE, which is provided by STM Electronics from European group of company. So basically, we are what we do in this we do is we predefine the ADAS things. Then we use the predefiners in ADAS.c. We predefine the ultrasonic function, and then we use ultrasonic C as a function. So basically, we use main fault header lines, and then we use in C. So first we predefine the function, and then we use in the C programs, and then how we run this program by clicking the right click and build the project. So yeah, this is how the project works and how the microcontroller work. Let's talk about the problem and solution. So current challenge is no unfitted monitor system. Battery status is difficult to track. Motor overheating may be ignored. Blind spot reduces safety. Fault are detected too late. So this is the challenge we are facing in current scenario of EVs and many electric vehicles. If we not talk about EVs, the blind spot problem is everywhere in many vehicles. So currently we managed to build a program by this internship that which we managed to do, like understand the how to reduce the driver load, how to understand the collision problem, how to understand the fault, what kind of fault it is, if it is from the engine side, it is from and many more things. So yeah, and what we are preparing from solution is live EV dashboard, real-time data monitoring, collision and blind spot alerts, and instant fault indication in UART-based communication. So these are the solution we are getting from this formation of microcontroller simulation and codes. The project objective is to understand the design of STM32 and read the sensor input, calculation EV parameter, implement ADAS, display the live dashboard. The design of STM32 we are using like IDM of Cube IDM, which is a workspace. We will provide STM32 in coding. Read the sensor will help us to read the sensor like input sensors, potentiometer and many more. Calculate the EV parameter like compute the speed, state of charge, torque, and range. Implement ADAS, detect the obstacle, generate the warnings. The ADAS implementation help us to understand how the blind spot vehicle is moving and how the collision time is, how much is collision time before they will collide to each other, and how to make a perfect distance and reduce the speed. Display the light dashboards like transmit visualize data in Python. We used visualize software like Visual VSPE, which will act as a wire between the Python and the data transfer, which is none other than Pixim Lab. So we are using hardware and software. The hardware currently using is STM32 Bluepill, STM32 Bluepill, Python. Um, Python is a software. If we count it in software, Virtual COM, which is also software. Only the STM32 is a software, and the sensors which is using in it, and potentiometer like pedals act as a pedal. STM32 Blueprint, ultrasonic sensor, potentiometer, and extra all are used as a sensor instead of a real car to simulate the data, to simulate the data, to simulate the data from the real world scenario, like how to act if a car come in front of a EV car, and how to manage the speed, how to manage the temperature, and how to act if there any fault. So basically, these are the software list, and this is the hardware. We are using STM32 Qubit software, which is this, and SchemLab, which is this, and Teratum, which is the thing we will use to communicate with the our code. ComCom as act as a wire between the Python dashboard with act as a wire between Python dashboard act as a wire between Python dashboard and our data provider, which is Pixum Lab. And then we use hardware STM Pure Bluepill, ultrasonic sensor, potentiometer, LEDs, which we can see here. You can see LED, potentiometer, and ultrasonic sensor, and many more. And these are the configuration we are using in our Bluepill. Like you can see it here, 8 megahertz, a QM CPU MIPS, which is 31.2. If we open this, the configuration, we can see this, the serial COM4, 1235, 503, and many more. And we get the output from by using the spare parts. You can see that we're getting the virtual our output in the terminal. EV parameter. If the vehicle consuming the battery by 25 watt hour per kilometer, then it is said to be in eco mode. Normal mode, it will consume 30 watt hour per kilometer. In sport mode, 35 kilometer power per kilometer. So we are using the battery capacity, which is about 12 kilowatt per hour, and torque range, which is 80 minus 80 nanometer to 250 nanometer. But I excluded the range because currently you can see that I'm using the range. If we provide the torque, which will reach to 2000, because I'm using the load currently is 1000. I'm using the torque currently highest is 2000 nanometers. The core equation calculation, voltage, battery, state of charge, estimated driving range, time to collision, and ultrasonic distance. So this all are the formula we are going to use to get the data of our state of charge, estimated range, torque, acceleration, brake, motor temperature, alarm, fault, UART, and distance between the vehicles and the speeds. So testing and future of scope is system validate via STM32, simulate an end-to-end UART element to Python dashboard, implement the collision blind spot detection with alarm and real-time visualization, future integrate CAN buses and real-time logging, OTA and advanced SOC, and many more. So basically, if I will interpret this in simple words, then I will use that STM32 simulation we are using to simulate our data to code the STM32 Bluepill microcontroller, and we are using IDM to simulate the data. We are using IDM to code the STM32, and we are using STM32 simulator, which is none other than Bluepill Scheme Lab. And we are managing to use Python dashboard, which will we get the data as real-time car dashboard. We are implemented the collision blind spot detection and alarm and real-time visualization. And further, if we can see that what we are going to use with this internship and what we are going to use with this kind of understanding of EV and ADAS is will integrate the CAN buses, real-time logging, OTA updates, and advanced associations of charge and algorithms and field testing of prototypes of EVs like currently we are seeing the world. So in simple word, I can conclude in simple word I can conclude that we can, if we improve the things, we will manage to get a future where we get if we where we get a pure energy EVs, which will help us to reduce the global warming issues and help the environment by reducing the current fossil fuels environment and reduce the carbon dioxide emission and many more things. So yeah, all from the PPT side. Let me show you the project and dashboard we have created. So this is things we are using currently. So if we manage to pull the things, we will get the warning and fault both as two, and we can see it on dashboard. Let us wait, and here it is. It will so that it will collide if we will don't manage the don't manage the total safe distance between the two cars. And this is the speed. This is the critical fault provided. UART connected. See a critical. The alarm type is critical. Motor temperature, brake, acceleration, and torque. And graph of speed. Let me expand it. This provide data. This let me. I, this is the potentiometer bar of temperature. If we increase the more temperature of motor will increase. As you can see it here. Let here it is. It provides temperature high by increasing and decreasing by the potentiometer. It will increase the acceleration. It will reduce the brake. You can see that it will reduce the brake. It will increase the acceleration and reduce the acceleration in same time. It will increase the and decrease the charge of the charge of the battery present in the EV vehicle. The it will tell us fault. It is where tell us about the critical condition or alarm. It will for right side, left side of blind spot, right side of blind spot, front sensor, left sensor, right sensor. If we reduce the distance between use this, you can see that it will give the bird eye view give us warning about the collision in blind spot. And here and you can see that here the dashboard of EV formed by the Python by using the Python dashboard, so Python programming language, and form a dashboard of real-time EV and how it works. Torque, acceleration, brake, motor, temperature, alarm, fault, and UART. Drive mode normal. If we increase speed, it will change according to it. And that's all. So here we are using this microcontroller, spare parts, virtual readings. We are getting IDM code generator to we can use it like build project, lean project. And then after creating the project, we can use the binary file to upload in the Prism by using the load binary and putting the value in it like ev-bin and open it. So yeah, this is command prompt we are going to use to activate the dashboard. And this is the command I used to activate the dashboard. And this is all about my internship. And thank you to Airtex MRText to provide me opportunity to understand the EV and ADAS ecosystem and all of the things like simulation and code generation. Thank you.